All right, ladies and gentlemen, this is the inaugural presentation, Open Science Presentations. My name is Ben Meekins, Research Assistant Professor at the University of South Carolina. It seemed appropriate for me to do the very first presentation. We're going to do this. It's reasonable for me to be the guinea pig. And so today I'm going to talk about comparison of sulfur dioxide oxidation on a platinum carbon and gold carbon catalyst for the hybrid sulfur cycle. This is a project that we're working on at the University of South Carolina in collaboration with Savannah River National Laboratory. And they've been partners in this with us for a number of years, actually predating my time at the university. And it's covered a wide berth of areas within this field. And so I'm going to give a little bit of background and talk about the actual work that we did and some of the work that's kind of ongoing and where this work goes as part of the broader overall picture. So first, a little background. So the hybrid sulfur cycle, the goal was to develop a way to produce hydrogen and oxygen from water at a large scale. So most people are familiar with electrolysis of water. And that works well, but you are limited by basically size and the rate at which you produce this. And you have to sort of continuously flow water in, you have to get the hydrogen and the oxygen out. And it works well, but there are ideally ways to do it at an even larger scale. And so one of the ways it was developed was actually from Westinghouse in the 1960s and 70s. They developed a way to, they developed this two-part cycle, and it was one of a number of thermochemical and electrothermal cycles where the overall reaction is water being split to hydrogen and oxygen. What you actually have is a two-part process. One part is relatively low temperature, a sulfur dioxide depolarized electrolyzer running at around 120 degrees Celsius. The other part is actually a sulfuric acid decomposer. So what you end up with is the net reaction of water being split into hydrogen and oxygen. But what you actually have is an internal cycle. So you have sulfur dioxide and water forming sulfuric acid. You take that sulfuric acid, you decompose it, and you get water and sulfur dioxide back, but you also get oxygen. And that's sort of the key step here. So, at each part of the step, you extract the hydrogen and the oxygen, and you cycle this sulfur dioxide, a little bit of water, and the sulfuric acid. And the nice thing here is, once you get it started, the only real input is a little bit of water. Otherwise, you're just running this cycle continuously, generating hydrogen and oxygen pretty much as long as you want. So the pilot plant actually did pretty well. It demonstrated a 150 liter per hour capability, which, if you're at all familiar with initial technologies, to be able to scale it up to a pilot plant and actually have it work well is pretty incredible. But, this was when oil was still very, very cheap. And so economics functionally doomed the process. With all the capital costs and with the fact that the technology was new, economically it wasn't feasible and it wasn't attractive enough to continue being developed, at least industrially. But as science is wont to do, it continued largely from two researchers, Lou and Ammon, throughout the 1970s, dropped off a little bit in the 1980s, and then picked back up in the 1990s, and more recently, as mentioned at the beginning, throughout the 2000s, throughout the late 1990s and the 2000s, and into the 2010s, the University of South Carolina has been actually, again with Savannah River, kind of at the forefront of this technology. Really pushed it a lot further than it was. I'll talk a little bit about that. So what we're going to focus on in this talk is the low temperature step. So the electrolysis is one of the key points of this cycle, and you want to try and reduce the voltage that's required while maximizing the current density that you achieve. And so what that means in terms of economics is you're paying less to power it. And so the less you have to put in to run it, the more economical it is. And the closer you get to the overall goal, which is hydrogen being produced at $2 per kilogram. That's the big DOE target that was actually developed with the help of SRNL doing techno-economic analysis. That's what you need to hit for this technology to be feasible economically compared with, say, steam reformation or even just putting it head-to-head, something like natural gas. That's what you've got to get to. And so to hit that with, again, a number of assumptions, you need to achieve a current density of 0.5 amp per square centimeter at 0.6 volts, and you need to produce a product stream of about 65 weight % sulfuric acid. The product stream needs to be that concentrated because that's what you need to have the decomposer step run efficiently. And so if you produce a product stream that has a lower concentration than that, you're going to have some concentrators before the actual decomposer. Any additional equipment is additional capital costs. It's an additional point of failure. And so that's a sort of a key thing is you want to be able to put out a product stream with an ideal concentration. The current best achievement in terms of the cell voltage is 0.66 volts. And that was done here at the University of South Carolina. But the acid concentration at that potential is not known. And so that's, it's a step in the right direction. The voltage has steadily come down from, starting at around 1 volt to about 0.9, 0.8, 0.7, and it's now been pushed down to about 0.66. Throughout the four or five decades of research, a number of catalysts have been explored: platinum, palladium, gold, iridium, ruthenium, their oxides, chromium, mixed metals, pretty much any noble metal catalyst that you can think of, and things like iron have all been looked at. Platinum is won out so far. There are some, like palladium, that were more active, but their stability was very, very poor. They wouldn't last more than a few minutes in the actual doing the actual reaction. And so that's, of course, not any good at all. You need a catalyst that's both active and stable. And so that's why platinum is won out, as it tends to do with a lot of electrocatalysis. So one interesting thing is that pretty much all the catalyst studies in the literature have looked at bulk materials, not nanoparticles. And for those who are not familiar with it, nanoparticulate catalysts tend to be much more active than their bulk versions. Gold is a fantastic example of this. Gold in its bulk form is more or less inert for the overwhelming majority of catalytic reactions. Once you make gold a nanoparticle, you get it down to a diameter of about 100 nanometers or less, it suddenly becomes very, very active for a number of reactions. And as the smaller it goes, the more active it tends to be up to a point. And so that was one of the things that we wanted to consider was, in addition, we know platinum should be a good catalyst because it is active both as a bulk material and just tends to be more active as a nanoparticle. But we needed to see if there were any other materials that might beat platinum out, given the cost that's associated with platinum, in addition to its relative scarcity. So we started out doing catalyst screening, and this was a thin film screening, so not exactly nanoparticulate, but this was more just to give us a starting point and to try and quickly eliminate materials that we would not be interested in looking at. And as you can see, we have a voltage versus current density plot here, and the main takeaway is that platinum and gold had the lowest onset potential for the reaction and had the highest current density as well. And so that's the two main things that we were looking for here. See that palladium actually performed pretty well, but as I mentioned earlier, the stability is non-existent, and so we didn't even mess with that. And similarly, iridium, the performance isn't terrible, but the current density is about an order of magnitude lower, and the onset potential is about 150 millivolts worse. And both of those are not acceptable. We also wanted to consider whether or not some kind of combination, given that gold and platinum were very similar in terms of the onset potential, we considered whether a mixed metal catalyst might be worth looking at. But as you can see here, regardless of the voltage that we used, we looked at both 0.1 and 0.6 volts versus a silver-silver sulfate reference electrode. In both cases, pure gold was the highest, had the highest activity. So again, we looked basically at pure platinum and pure gold. Did not mess with any of the mixed metal, bimetallic alloys or anything like that. So for the experiments, we had two types of experiments that we did. The first was a rotating disc electrode, which is letting us look at the catalyst activity directly, removing as many outside sources of error as possible, and basically letting us look at the catalyst in a very controlled environment. And the second was actually putting the catalyst into an electrolyzer and running it under conditions that would be similar to what you would actually need to run it under for practical application. And so you can see down here at the bottom pictures of the gold and platinum catalysts. Both were very small. This figure here shows the particle diameter. The gold was on average about a nanometer or so smaller than the platinum, but they were both very similar in size. And so, we made sure that we had catalysts that were reasonably close, so that size effects shouldn't be a big issue here. So with the rotating disc electrode, we used a glassy carbon tip because it's both stable and inert for the sulfur dioxide reaction. We used 4 different concentrations of sulfuric acid, 1 molar, 3.5 molar, 7 molar, and 9 molar. And what those represent are effectively the startup and then approximately the steady state of what an electrolyzer would run under. And the reason we do that is we need to see how the concentration of the sulfuric acid actually affects the performance of the catalyst. And that could be a couple of different ways. First of all, it could be that the sulfuric acid just acts because its viscosity is higher. Sulfuric acid could just slow down diffusion of the ions to the electrode, which would in turn lower the apparent activity of the catalyst. On the other hand, sulfuric acid could actually cause a reduction in activity of the catalyst via damaging the catalyst itself, or by attaching to the catalyst surface and occupying catalytic sites on a longer scale basis, whether it's permanent or a time scale that's much longer than the typical reaction time scale. And so we need to understand how sulfuric acid concentration affects that, because that's going to affect the actual operation of the electrolyzer. So we had 2 choices in terms of how to introduce sulfur dioxide to this rotating disc electrode experiment. One way would be to saturate the solution with sulfur dioxide by bubbling sulfur dioxide through this acid solution. The other was to use an analog, in this case sodium sulfite, and that's what we chose to go with because when you have sulfur dioxide in water, it almost immediately forms sulfite anyway, and this way we could very easily and very consistently and repeatably define the known concentration of sulfite in solution, instead of having to worry about where the equilibrium centered, how that changed with acid concentration, because it would. And so this let us know every single time exactly how much sulfite was present. We used a platinum counter electrode and a silver chloride reference. And we used a consistent loading of 27 micrograms of the catalyst per square centimeter. The 2 catalysts we had were commercial. The platinum was 40 weight percent and the gold was 20 weight percent. But again, we normalized the loadings of the metal itself, so that was the same throughout. With the electrolyzer, on the other hand, we used a proton exchange membrane style cell. And for those who are not familiar, that's basically a graphite cathode and anode, a block with a polymer membrane, or it could be a membrane made of other materials. Typically, it's a polymer membrane that separates the 2 sides. And the function of the polymer membrane is to allow only cations, in this case protons, from the anode to the cathode. Electrons are forced to go through the external circuit where they do work, and then they recombine at the cathode with the protons and do some kind of reaction. It could be oxygen reduction. It could be hydrogen formation. In this case, that's what we're doing. We're forming hydrogen gas on the cathode. We feed sulfur dioxide as a gas to the anode, and we also fed a small amount of water through a nebulizer on the anode. You need to have some water present. We used a Nafion polymer as the membrane. Nafion conducts protons, but it needs water present to maintain that conductivity. If the Nafion gets too dry, conductivity tanks, and your cell resistance goes up dramatically, which means you have huge voltage losses across the cell, which means you need to put more voltage in to achieve the same current density. And so you have to manage your water very carefully. The loadings of the catalyst that we used for both platinum and gold were 0.1 milligrams per square centimeter of metal, 0.1 milligrams of the metal per square centimeter on the anode, and we kept a consistent 1 milligram per square centimeter of platinum on the cathode. That's more than enough loading to ensure that the cathode is not a limiting factor for the reaction. So we know that any difference that we see in cell performance of the electrolyzer is due to the difference in the catalyst that's on the anode. And as I mentioned, the Nafion needs water to maintain its conductivity. To achieve that in this case, we just fed liquid water to the cathode and just flowed it continuously throughout the experiment. So this is the summary of the results from the rotating disc electrode. So there are two main takeaways here. The first is that acid concentration does make a difference. You can see that as we go from 3.5 molar to 7 molar to 9 molar, there's a pretty significant drop off in the amount of in the limiting current that's achieved. Now, the fact that they both drop off means one of two things. Either the catalyst itself is affected by the higher amount of sulfate present, and or the diffusion of the reactant is slower. We know the viscosity of sulfuric acid is higher than that of water, so the diffusion aspect is one part of it. However, because we're using a rotating disc electrode, we also know that at the steady state value at least, diffusion is no longer the limiting factor. If you spin a rotating disc electrode fast enough, you hit a limiting steady state current, and that lets you compare two materials even when diffusion is changing depending on your electrolyte. And so the second thing that's apparent is that gold in all cases outperforms platinum. The difference between the two does get less as you increase your sulfuric acid concentration, but in pretty much every case, the limiting current is higher at a lower potential, and that's what we're looking for. The other big thing here is when you extract the kinetic currents, interestingly, excuse me, the platinum kinetic currents, so the actual current due to the activity of the catalyst, is relatively unaffected by the concentration of the acid until you get to relatively high potentials. With the gold, on the other hand, there's a very clear difference between the three of them. And so the crossover where gold becomes better than platinum does change depending on the voltage at which that occurs changes depending on the concentration. And so that was kind of an unexpected effect that's not necessarily apparent from the steady state current diagram. And so, it was something that was kind of interesting to see. And then the electrolysis itself, what we find is that similarly to the fact that on the rotating disc electrode, the gold had higher current density at lower potentials, we see the exact same thing. So this gray trace here is platinum, the black one here is gold. And so you can see that, pick 0.5 amp per square centimeter, the gold on carbon hits that at around roughly 0.77, maybe 0.76. Platinum doesn't hit that until about 0.86 to 0.87. So we're looking at somewhere in the neighborhood of a 100 millivolt difference. And in electrocatalysis, that's a huge difference. So in terms of the conditions here, we held the temperature of the cell of the electrolyzer constant at 90 degrees. The scan rate on the current potential curves here was 0.1 millivolts per second, so very slow, which effectively allows us to find a steady state value for each potential. And that is important because if you scan it too quickly, it does take an electrolyzer, because it's around, in this case, it was a 50 square centimeter electrolyzer. Excuse me, it was a 10 square centimeter electrolyzer, but it takes some time to reach an equilibrium every time you change the potential that's applied or you change the current that's applied. And so you have to scan it slowly enough that you can allow the system to equilibrate, and scanning at 0.1 millivolts per second achieves that without forcing you to, for instance, do several individual points and tally the data up yourself. We flowed 165 standard cubic centimeters of sulfur dioxide and 3 milliliters per minute of water on the anode, with 1.7 milliliters per minute of water on the cathode, and this was with the Nafion 115 membrane. So it's around 50 microns or so in diameter, or in thickness. The other thing here is, if you look at the right graph, if you take out the voltage loss, the voltage increase due to IR drop, the difference between the two actually gets a little bit bigger. In this case, gold beats out the platinum by around 125 to 150 millivolts. So again, that's a significant drop in terms of electrocatalysis. And this red line signifies the point of interest. That's the half amp per square centimeter goal that we're trying to achieve. Now, we didn't hit the potential that we want to get to yet, but this represents a big step in the right direction. Stability, of course, is another key point here. You can have the best catalyst in the world, but if it doesn't last more than 5 seconds, it's not very useful to you. And so what we find is that with platinum and gold, if you're above 0.85 volts, you actually get good stability from both of them. Over the course of an hour, they both basically maintain their activity. Gold actually even went up a little bit. But you can see here at 0.95, gold is same potential. Gold has much higher current density. And the same holds true as you go down to 0.85 and 0.75. But more importantly, gold maintains its stability at these voltages, whereas platinum, once you go below 0.85, it drops off very quickly. This drop off is recorded after an hour, but in practice it takes something more like 5 minutes, 5 to 10 minutes to see the drop off happen. And you'll see an immediate loss of activity. You can sometimes get it to recover if you reapply a high potential, but as soon as you go back to the lower potential, you'll see the drop off happen again. So there's some major conclusions here. First, the carbon-supported gold nanoparticles clearly outperform the carbon-supported platinum nanoparticles that are traditionally used in terms of both activity and stability, which is great because gold is a little bit cheaper than platinum, and so that it makes it of interest to us. Nafion membranes will not be able to achieve the benchmark of half an amp per square centimeter at 0.6 volts. The reason they can't do this is they cannot handle the high acid concentrations. I'll talk a little bit more about this in just a minute, but the short version is that the membrane resistance goes up exponentially as the acid concentration increases. So what we're going to have to do is look at some alternative membranes, such as one sulfonated polybenzimidazole. I'll talk a little bit about that as well. You're going to have to switch to something like that that can handle both high acid and high temperature environments to hit the benchmark that you're aiming for. Thirdly, you can actually use rotating disc electrode experiments to reasonably predict electrolyzer performance. You may not know exactly how well it's going to do, but if you need to compare two catalysts or two preparation methods or something like that, you can use RDE experiments to have an idea of what you should expect, and you can use it to eliminate certain materials. As an example, we considered silver because there are some theory predictions that say that silver should perform as well as gold and platinum do in terms of catalytic activity. But what we find is that after the very first cyclic voltammogram with silver, the silver is completely dissolved or just reacts with the sulfate in solution. And so what you end up with is a catalyst that very quickly disappears. So moving forward, one of the things that we're trying to do is develop a model of the hybrid sulfur electrolyzer that will allow us to figure out what it is that we need to actually target to try and hit the DOE's $2 per kilogram target with, half an amp per square centimeter at 0.6 volts. Because there's a lot of different things that are going on there. You can change out the materials, you can change out the catalyst, you can start playing around with the temperature, with the current density, with the amount of water that you're putting into the system, things like that. And so the problem is those don't act independently. If you change one, you're probably changing at least 2 or 3 other ones, and that's going to have an effect on the current density you can achieve, the potential that you need to apply, and of course, something I mentioned at the beginning, the acid concentration that you produce. If you hit 0.5 amps per square centimeter at 0.6 volts, but you're only producing, 10 weight percent sulfuric acid, that's not sufficient. And so that's not going to cut it, and you have to be aware of that. And so what we find here is that we've got this experimentally validated model that Dr. Max Gorensek at Savannah River National Lab has been working on. So he's taken our experimental data and developed this model that lets us predict, choosing to fix certain parameters, what we need to be targeting to try and achieve our goal. And so this one figure is kind of the big takeaway here. And what it actually shows is that we can hit, at least in theory, the target of 0.6 volts at several different current densities. So the one that we're aiming for here is the 0.5 amps per square centimeter. And the theoretical model says that we should be able to achieve that if we can raise the temperature of the electrolyzer to approximately 127, 128 degrees Celsius. So we can call it 130. But what it also tells us is that if we can go to 135, 136, we should be able to actually hit a higher current density at the same potential. And it goes off the chart here, but 1 amp per square centimeter should be achievable at lower than 145 degrees Celsius. And that's a kind of a big deal because obviously if you can exceed the target, then you get even a little bit more flexibility in terms of maybe what the product stream needs to be or some of the other economics of the overall cycle. Anything that gives you more flexibility is a good thing. The big key here is you have to pay attention to your water stoichiometry. So you have to pay attention to how much water is being fed with the sulfur dioxide. And what we find is that as the temperature increases, and in particular as you get above the boiling point of water, so when more water is entering the vapor phase, you actually have to feed more water in to achieve the current densities that you're trying to achieve and at the potentials that you want with the concentration of the acid that you want. Because what happens is, as the water vaporizes, more of it tends to stay in the vapor phase as it flows through the cell, which means that the acid concentration locally on the catalyst goes way up. And it turns out that sulfur dioxide is actually less soluble in more concentrated sulfuric acid. And so effectively what you have is you get a lower amount of reactant at your electrolyte or at your electrode, which means that your current density tanks. And so you actually, it's a little bit counterintuitive. You think, oh, I'm just going to jack the temperature up on the electrolyzer. That should make it work better. Well, it does to an extent. And so that's kind of the big thing here is that we see that both cell temperature and water control are what we have to pay attention to while we're doing this reaction. And so you can't just change one thing and have it work. You have to pay attention to how everything plays together. The other big thing here is the membrane separator. So I mentioned in the work that we've done, we've been using Nafion, but one of the other things that we've been looking at is a sulfonated polybenzimidazole polymer membrane that's been developed in the Benzowitz group at the University of South Carolina. Dr. Brian Benzowitz is in the chemistry department. If you need to know anything about polymers, he is your guy. He is very knowledgeable, his group's very knowledgeable, and they've developed a number of these polybenzimidazole membranes for a number of different applications. They've done phosphoric acid cells, hydrogen pumping, hybrid sulfur. They're also helping us with some other projects on electrooxidation of hydrochloric acid, hydrobromic acid. And what we see, one of the big keys with these PBI membranes is that they are acid and temperature independent in terms of their conductivity. So what that means is you don't have to have an excess of water to maintain your conductivity. You can actually put this thing into 8, 9, 11, 12 molar acid, which is what you need to get up to, and it will keep its same conductivity. And the conductivity in this case is about 0.05 ohms square centimeters, which is really good. But as you can see with Nafion, as you get to about 6 molar, with even a thicker membrane here, you start to see this exponential increase. Similarly for the 115, it's a huge increase, and you're getting up to easily an order of magnitude higher resistance. And of course that means that you have added voltage loss, and so to achieve the same current density, you've got to apply more potential. And so this SPBI membrane is one of the other big steps that we're taking. And going back to this figure, that's what this assumes. This assumes that we're using the SPBI membrane. We've started working on it, and it is better. You don't have to flow any water at all to the cathode. You can very carefully control the water on the anode, which means you have much better control over the acid concentration coming out in the product stream. And most importantly, it removes one of the major issues that you have to deal with when you work with Nafion, which is water management. You don't have to do water management this outside of controlling what you need for your reaction on the end. That's it. The PBI is incredibly stable. The Benzowitz group did a years-long study of leaching of the sulfuric acid that they actually put into the membrane that gives it its conductivity. And after several years, it had lost less than 5% of the acid that was in there, which is just incredible stability. Similarly, they have no problem with temperature. They actively run it in fuel cells up to 200 degrees Celsius, and it again runs for hours, days at a time with no issues. And so that kind of both acid stability and temperature stability is a huge thing, and so that's going to help us moving forward. And so finally, I'd like to acknowledge the co-workers. Dr. John Widener has been a mentor of mine. He's actually at the University of Cincinnati now. He's the new Dean of Engineering there. Well suited for that. He's a fantastic person. John Weiss and Varsha Gopal were two undergrads who worked on this. Both of them carried out experiments, especially on the rotating disc electrode. They were huge helps there. Dr. Hector Colon Mercado at Savannah River National Lab is the experimentalist that I worked with, and he did a lot of the electrolyzer work on this. He and I both have electrolyzers set up, but his had a little bit more control, so we used his work. And then, of course, Dr. Max Gornsek is developing the model, and we actually just got that paper accepted, pending some revisions, and so it will hopefully be published soon. If you're interested in reading about the experimental work that I detailed here, I've got a link to the paper listed here. I'll also have it posted below the YouTube video of this. So please feel free to check it out. And with that, I will take any questions that anybody has. Hey, yeah, no problem. Like I said, there's a lot going on. It's a complicated, it's a complicated topic. Yeah, yeah, there's a lot happening with it. Is there anything I can help you understand better? I'm impressed. 8 pages of notes, damn. And A1 Bear, I see you there. If you have any questions, feel free. Otherwise, thank you for stopping by. I guess it's good that I didn't. I was going to include a few more slides on the model. It's probably good that I didn't. So yeah, SPBI is the best that we have right now. So yeah, that actually came up or not. I didn't know. Wait, hang on one second. Something. Try doing the question one more time. Uh-oh. All right, question bot's not working. Mess with that later. But to answer your question, yeah. So PBI, the sulfonated PBI is the best polymer that we have that we know of right now, because it's impregnated with sulfuric acid. We don't have to worry about leaching, and it also happens to like I said, it maintains that conductivity even without water. We actually are doing some work. The hydrochloric acid electrooxidation I mentioned, we're actually just flowing the HCl by itself. There's no water anywhere in the system, and we can still get about a 0.5 amp per square centimeter of current density. We should be able to get higher. That's something we're working on now, but that's a ton of current flowing even with no water anywhere in the system. In this case, we have a little bit of water. In terms of others that, and the SPBI, the Benzowitz group has just started working on a thinner version of it. So they're calling it this basically Gen 2 of the SPBI. It's one of the major issues with the current SPBI is that it's more like a gel polymer, and so when you compress it in the cell in the electrolyzer, if you don't have everything set up exactly right with the sub gaskets on it, or with the gaskets that basically seal it, you can actually have your reactants, whatever you got flowing through the anode and cathode, leak around the edge of it, and so of course that's going to completely screw up your experiment. The second version, it's more like it feels more like cellophane, and so it doesn't have that same issue with compressibility, which is great for us because it removes one potential source of error. That was one of the major issues we had with the HCl, was we would compress it and then the HCl gas would basically run around the outside, and so we'd see little drops of this kind of yellowish acid as it slipped outside the, not all of it, but some of it would slip outside the cell. In terms of stuff that we could theoretically achieve the same results with that we haven't tried, I don't really know enough about the polymer membranes to be able to tell you that. I know that Dr. Benzowitz's group is still working on it a lot. They have a lot of different variations, and so what they're trying to do right now is figure out how to, and one of the things they've sort of achieved with their newest version of it, is how to have enough solid polymer material to have the structural, temporal, and temperature stability that we need, but still maintain high conductivity. And so that's kind of what they're working on. I don't know off the top of my head if there would be a better, even just in theory, a better material that would work for what we need at this point. And yeah, it's very surprising that it maintains its stability, even like I said, up to 10 to 12 molar. But that's what we need. There's some indication that we might be able to get away with a 50 weight percent sulfuric acid product stream, which would be great, but that's kind of remains to be seen. Videos or literature, yeah, I'll send you some links. So I can send you some of the older papers out of the group that would provide you some background. Videos, I don't know if there are any. I'd have to actually look around and see. But there's a couple of sort of key papers that you could look at. So like the Liu and Ammon papers, they had a nice review article. I forget exactly when it was published. I want to say it was somewhere in the 1980s, maybe 80 or 81. So that would cover all the early work that they did. And the two of them were at Westinghouse. They were the ones that really pushed a lot of the stuff to sort of set the baseline for all of it. After that, honestly, a lot of it would come from work research at the University of South Carolina. So like Dr. Widener, the guy I mentioned, and thanks as my mentor, he did a ton of it. He's been working on it for probably 15 years, 20 years at this point. So he's done all variations of it, everything from theoretical to experimental, all the different parts. Playing around with anode and cathode materials, compressions, polymer membranes, catalysts. Going from liquid phase to gas phase was one of the main things that he did. Because originally people would just, you would like bubble the sulfur dioxide in a water stream and run that into the cell. And so, and that works, but your fusion rates are orders of magnitude lower. And so by going to gas phase, that's